Okay, guys. So in this lecture, I want to talk about finding the volume of a solid of rotation, but this time using a different method because maybe the disk washer method is not the best choice for calculating the volume in the situations I'm going to tell you next. So consider the following case that, like, suppose you have a function that looks like something like this, or a part of a function that looks like this. Now, this could be very simple, like part of a parabola, like say y equal to x minus 1 squared plus 1. So it would be like this is the vertex of the parabola, and that's what it looks like. And suppose I'm rotating it about the y-axis. What would happen when I do the rotation? It's going to look like something like a, a double bump. There is, it's like it's a donut looking from the above, but there's a meeting in the middle. So it would, if I wanted to do the disk or washer method, then the rectangles would look like this, right? That's what the rectangles look like. The problem with the rectangles that are going to turn into washers, the problem with those rectangles is their height of those rectangles. This part, the bottom bound and the top bound are the same function. So I cannot really try to do a disk washer method with this because it's the same function as your upper and lower bound. So it's kind of like you hit a wall with this one. So it's not that it's not doable completely. I have to kind of say that just so you guys know that there is a possibility to do this. So again, if this is my shape, the half parabola, I can break it into pieces and calculate the volume of this piece after it rotates, and I can do washer method with that. And then I calculate volume of this piece after it rotates, and I can do washer method for that, and then I can add the two of them together. But you can imagine how much work that is, which is not a very optimal thing to have to go through if there is a better way of doing it. And of course, there is a better way of doing it. The way we're going to look at it is it's very intuitive, but again, it's nice to see it formulated and worked out. So the way we're going to work at it, say, okay, if you rotate this, you're going to get something that looks like that. So you're going to get rectangles that, if I flatten it out, there's rectangles that go around. So and this would continue going all the way up and create what we would see is as cylindrical shells. These are shells created by rotating rectangular pieces about the y-axis. So it's kind of like a shell of a can, like maybe a can of corn, or if you're thinking about it, but a lot thicker shells. Like, don't think about a very thin shell, like about thicker shells. Of course, we're going to take the limit as those shells get really thin. But to begin with, the shells are going to be thicker. They're going to be thicker. So how do we calculate the volume of those shells? And then, of course, the idea is that you calculate the volume of each shells, then you take the limit as the thickness of the shells go to 0, or the number of shells go to infinity, and then that would give you the total volume. I used to tell students, if you think about onion, if you think about an onion, for example, you can calculate the volume of onion by just slicing it from top to bottom, and you get just these discs, and you can calculate the volume of those discs. Or you can take out the shells of the onion and calculate the volume of each of those layers, and then add them all up, and you get again the volume of the onion. So you have two ways of calculating the volume of onion: either slicing it from top to bottom, create those discs, or you can take out shells or the layers of the onion and add those together, and that would also give you the volume of the onion. So if I am doing calculate the volume of the shells, want to calculate the volume of the shells, basically, if I have a, say, two radii, one radius that goes from, say, onto Ri, and then another one would be Ri plus 1. So let's say This one is Ri. This one is Ri plus 1, because again, you're going out. It could be Xi plus 1, of course. Then the volume is going to be the outside volume minus the inside volume. So it's going to be the outside volume is pi Ri plus 1 squared, and then your height, and then minus pi Ri squared. This is height I plus 1, this is height I, whatever it is. Now I'm going to write this in terms of the function values and the variables. So if this is again my function, and I keep drawing it and it doesn't take away from the explanation, but let me just have a clean picture. If this is the same function, say for my example, f of x equal to x minus 1 squared plus 1, then the Ri's, the role of the radii is played by the xi and xi plus 1, because those are the partitions. The role of the height is f of xi and f of xi plus 1, but since I'm flattening it, I could just use f of xi. So the volume of the shell, the ith volume of the shell, is going to be, and again, it's approximated because we're flattened the top, so it's approximately equal to pi radius xi plus 1 squared, height f of, and I'm going to use the same height for both of them, f of xi minus pi xi squared f of xi. We're using both heights for that, same height for both, which is going to be pi f of xi plus 1 squared minus xi squared. Then I remember that I can write the difference of squares formula there. That's xi plus 1 square, xi plus 1 plus xi plus 1 minus xi. This, of course, you remember is a delta x. This I can multiply and divide by 2, and you're like, well, why do you do that? Well, because, so multiply by 2 and divide by 2. And if you're looking at this is xi, this is xi plus 1, the average of them would be in between xi and xi plus 1. So basically, as you take the limit as delta x goes to 0, that average xi plus 1 and xi will all fall on top of each other. So my Riemann sum, maybe I write the Riemann sum here so we don't veer away too far from the picture. My Riemann sum for the volume would be approximately sum I equal to 1 to n of 2 pi fxi. You could just write it in the terms of xi star, because you're picking some xi star in between them. And then this average would also be xi star delta x. This represents the height. This represents the radius. This represents the thickness. So it's going to be volume is exactly equal to limit as n goes to infinity of that summation. A lot of students have issues with xi star and so forth. And what I tell students is xi star is just some variable, some value in between in the ith partition. So that's all it is. And I don't worry too much about it, because once I take the limit, then that's just, they're all going to just fall on top of each other. So this really is going to be integral from a to b, and depends on what your bounds are, 2 pi x f of x dx. It gives you a volume. So in the case of my example, find the volume of the solid formed by rotating the area bounded by y equal to x minus 1 square plus 1 and the x-axis about the y-axis. So if you do it, again, it's going to be the integral. First, you have to figure out what are the places where the function cuts the x-axis, because those are your bounds. So for me, I let x minus 1 square plus 1 equal to 0, because your y is 0 at those places. Sorry, there's a minus. Okay, so you get x minus 1 squared is equal to 1, x minus 1 is plus or minus 1, x is 2 or x is 0. And those are the two places. Okay. Now, integral is going to be from 0 to 2, integral of 2 pi x, f of x in this case is going to be the function that we have. You can actually expand this if you want. You get negative x squared plus 2x minus 1 plus 1, which is just 2x minus x squared. Again, this is height, this is radius, and this is the thickness. And this integral, of course, gives you the volume. Sixteen third and 16/4, you get that. Which is really just 4. So for 16 minus 12 third, which is going to be 4 third. Okay, so that's the volume of the solid. Now, what would happen if I, instead of rotating about the y-axis, I chose to rotate it about the same graph, which we established it is 2x minus x squared. And let me rotate it about x equal to -1. What would happen there? My bounds don't change. The bounds still are from 0 to 2, 0 to 2, because that's how you're measuring where your function is. But your radii would be from here to whatever x is. So it's going to be x minus -1, which is actually x plus 1. That's your radii. 2 pi is still there. And your height is still going to be the same height, which is going to be 2x minus x squared. So this will affect your radius, doesn't affect your function part. It's just the radius part changes. Similarly, for the same graph, so again, because you're rotating about a different line than you did for the previous example. Now, if I do the same exact function, but rotated it about a different graph, different line, now let's say this time, same function, 2x minus x squared, and I rotated about the line x equal to 5, for example. Your bound doesn't change. Again, you get the same bound of 0 to 2, because that's where the function is. 2 pi doesn't go away. Your radius now is going to be 5 to whatever x is. So it's going to be 5 minus x. That's your radius. Your height is still going to be 2x minus x squared. Again, x is the variable you go through from 0 all the way to 2. Those are the x values. So if you want the radius of, and remember, you're turning this way now, right? If you want the radius of rotation, then there's a distance from 5 to x, so it's 5 minus x. So that's how you calculate that. Okay. So cylindrical shell is really, the two are not, there shouldn't be a huge doubt on which method you should use. I think it should be pretty straightforward that if the problem tells you use cylindrical shells or use the dishwasher method, then you're pretty much, your hands are tied. But if you could do either one of them, then you can just go with whichever you're comfortable with. Let me do another example. Now, this example is slightly different because in this example, I'm actually having, let me do it and then I'll show you what it is. So I have, let's say y equal to x and y equal to x squared. So that's the thing. So y equal to x looks like this, y equal to x squared looks like this. They continue, but this is the region that we're looking at. And let me rotate it about x equal to -1. So this is the axis of rotation, no problem. So, all right, so here's the important thing. And I'm gonna have to do with cylindrical shells. The question says use cylindrical shells. So this would have been okay. I would just do outer radius minus inner radius and done. But cylindrical shells have to be a little bit careful. The bounds are still 0 to 1. You remember we had this before. Your radius still is x minus -1, which is x plus 1, I understand. But the height is now different because now the height is going to be this for every x, which the height is going to be the upper function minus the lower function. The upper function is x, the lower function is x squared. So sometimes for your cylindrical shells, you actually have two different forms, two different heights that you have to subtract from to get the height of your piece, whatever that piece is. And of course, for this one, you foil it and then you simplify it as much as you can, and then before integrating. So how do we decide the y or the x? I usually tell students, like I draw this chart for students, saying if you rotate about anything that's horizontal, I'm sorry, I don't know why my chart looks bad. Disc, washer, and shells. Sometimes we refer to the cylindrical shells method as shells method. If you rotate about anything that's horizontal or parallel to x-axis, in the disc washer method, again, if you're rotating about anything that's parallel to x-axis, in the disc washer method, you're going to do your changes, your measure is going to be dx. But the shells method, if you rotate about the x-axis, you actually have to do dy. If you rotate about something vertical, which is parallel to y-axis, disc washer would be dy, shells method would be dx. So shells is always flip. Like look at this picture, the picture that I drawn earlier. I'm rotating about something parallel to the y-axis. It's a shell method, which means my measures are dx. In the previous lectures where we had disc method, if I was rotating about something parallel to y-axis, then it would be dy. So shells, if you rotate about anything parallel to y-axis, shells is dx, disc is dy. if you pair anything rotated with respect to anything parallel to the x-axis, disk is dx, shell is dy. So knowing whether you use dx or dy is half the battle, because you know the bounds are going to be with respect to those two, and you know that the functions have to be written in terms of those variables. But so I think this hopefully this diagram helps you a little bit. But as I said, it's pictures help, drawing pictures, knowing where the functions are, knowing which way you rotate and so forth. All of those things are factors that can be very helpful. But this step was kind of like a shorthand, quick way of telling you how to decide what measure you're going to use when you rotate them. So that's the discussion of cylindrical shells. There are other examples that again you can go with this. So my next video, I'm going to talk about some homework problems from these two topics. I hope I see some of them on the discussions. Otherwise, I'll just pick some problems I'm going to do on the topic of cylindrical shells and disk washer method. So I look forward to making that. I hope this was helpful for you.